going on. So we talk about this Cooper pairs circuit, right? So we start doing the quantization. First of all, what did we do? We define the flux in each branch. We use this definition, which is very familiar to you, V equal to d phi dt, right? Then we equate the KVL. So for the direction I made, it has to be VC plus VB plus VA equals to 0, right? So what should be the direction of VG? I think it is not clear in that paper, but I think it should be in this direction, which actually I forgot to explain why at the end in the last lecture. I will tell you again, right? If I do this, then VC is just equal to VG. So that's why I modify from the previous lecture from negative to plus, and then we have something similar, right? Anyway, we have the KVL. Then we have KCL. We know IB equals to IA. And we also define this capacitor, which is the CS per CJ. I hope you understand physically what it is. CJ is the junction capacitor of the Josephson junction because it is a superconductor insulator superconductor structure. It's just a capacitor in regular sense. And by the way, sometimes people try to test the superconductor Josephson junction at room temperature to do the screening because cooling time to dilution refrigerator temperature is very time consuming. And how do they screen? They find correlation between the quality of the Josephson junction and its leakage current at room temperature, which is just a capacitor leakage current, right? So this sum equal to C sum, right? And we just used all the knowledge we learned from electrical circuit. Total charge equal to capacitor times the voltage across it. And voltage here, of course, can be expressed as the time derivative of the flux, right? And another important thing is the equation of the Josephson junction. I hope that you get familiar with this. Critical current times psi phi A. Yeah.
By B and by C, like inductor on those lines.
Phi B and phi C, right? So it is just basically a quantity that obey this equation. So it's not the real magnetic flux. Yeah. So I should go deeper. I don't. Also, my limitation. So there is actually a theory behind all this formalism. I think it's at least referenced in this paper. You can take a look.
Okay.
Yeah. In the appendix, when it discussed this circuit, it said it will use the approach of that paper. I think it's about 2017 paper. Yeah. If you cannot find it, let me know. So actually, there are more systematic way when the circuit becomes very complicated. Now I just use a simple one. Okay, then what we do is just to do the substitution. The goal is what? The goal is that I want to relate it to the phi A here, because once I get the phi A, I have this equation of motion. And what is this phi? This phi is related to the generalized coordinate we are going to use, right? Because we know that phi is related to the general coordinate. That's why we want to substitute it so that I have this equation. Just like something times the acceleration, right? Because this is phi A dot dot, plus something with the position, like this is the potential energy, and then something related to the phi dot, right? No, this is also dot dot. Okay, now, so then we need to guess the Lagrangian, right? So what we just say that, probably this is the Lagrangian, but there's some reason that this is correct, that we guess it, just like last time you guys discussed, can we go directly to here? Right. So in this Cooper pair box, it turns out that, right, people try this formalism and it works. The position is the phi, and the velocity of course is phi dot, right? And then later you find that the charge is the momentum. But anyway, we guess this because look at this. This is just half capacitor times the phi dot, right? And phi dot is VA, right? Remember? This is the total capacitance. Phi dot, which is VA dot, so it is half capacitance times V squared. This is just like half capacitance times V squared. So this is the energy you store in this capacitor, right? So this is like, and then we also have this one, right? This is like the potential energy, right? But anyway, we just use the Lagrange equation. We show that, yes, if I have Lagrangian like that, I will get the equation of motion as what I derive here. Is this okay? And the reason I want to find the Lagrange equation is because I want to find the Hamiltonian. Because I know that Hamiltonian connects the classical mechanics to quantum mechanics. And then I use Hamiltonian to do quantization, right? So actually someone asked me in email about assignment 3, and that student forgot that how to find the generalized momentum. You actually find it for the pendulum, right? I put in assignment 3, question 3. You just do partial L, partial velocity, right? You will get the momentum. This is by definition, right? So here I use partial L, partial the velocity in this is phi dot, right? Because I told you that position is phi and the generalized velocity of course is phi dot, right? Then again go through a lot of math. In the video you see I make mistake because I actually need to remove the q dot or the phi dot in the Hamiltonian, right? So I should be patient. First of all, do all the substitution and then group everything. So I group phi A dot together here, right? And eventually, I forgot to mention this phi A dot turned out to this big term. I just use this partial derivative, right? Put in, and then eventually I get this term. Which I can further simplify as this one. So these are all math. Like, do you need this in your exam? No need. I am not going to. I'm not going to test your math skill. But I lay out this because I feel that when I study, I cannot find the resources and defaults. Defaults in the details. Very often, I just got stuck by one plus or minus or a factor. We don't know why. That's why I show you all these details. If you want to understand, you go through these details are good. But I still want you to be able to go through when you sit down with the paper. But do not be too scared. This is a lot of substitution. We should use mathematical instead of human, right? But you need to do this once in your lifetime, right? But anyway, the final result is that I find the Hamiltonian in terms of phi A and QA. And as I said, phi QA is the, what is that? The momentum, right? And phi A is the position, right? So I promote them to the operator form. So nothing special, right? So we've done so many things. We solved the circuit to find the equation of motion because we want to find the correct Lagrangian. We find the correct Lagrangian because we want to find the correct Hamiltonian. Once we have Hamiltonian, we have the conjugated momentum and position. I promote them to the operator. And then this one, again, will follow the commutation relationship, right, that we discussed earlier. So that is how we come up with this. Any questions? And we also further try to simplify. We say sometimes maybe C summation is much larger than CG. We can do that in the circuit, right? So then you will get this one. Now this is where I think the direction of VG is correct. Now look at what is QA and QG, right, in this case? QA is the charge across this capacitor, right? Because QA equal to C sum times VA. But when I have VA, which is positive, then QA is positive, right? Basically, it's talking about how many positive charge at this place. And similarly, what is QG? QG is just equal to QG is a little bit different. It is VG times CG, right? So this is not easy to see because we're talking about the VG here and then the CG across it. The real charge across CG is VB times CG, not VG times CG. So this is just a parameter, right? But however, when I put the gates here, look at this. If my gate is positive, I'm going to induce if it is drawn in this way, this is negative, right? And this needs to be positive, correct? So this formalism now is saying that if I have a positive charge here, then the total Hamiltonian is related to the difference between this charge of QA minus QG, right? Which makes sense because this is a background charge. It will correlate to the general formula I'm going to say later. So now I divide QA by 2e, number of Cooper's pair. Then my n is going to be positive also, right? But I can have extra Cooper pairs that can be negative charge. Just depends on how I apply the voltage. But the point here is that this one is, if I just think about positive charge, I divide both of them by 2e because Cooper pairs has 2 electron, right? So it's 2e. So the number of Cooper pairs will be QA minus QG in the orientation I just shown you. And then you will get this formula, H equal n minus ng to the square. And then here you need to multiply by 2e divided by 2c sum, right? This is the correct Hamiltonian people have been using. And that's why I think my derivation will be correct if the VG is having the positive terminal at the bottom. Because if you have this on the top, then you are going to have the plus here. And that is not what we usually have, right? So that's why I define in that way. But there's still a room for error. Just pay attention because that paper did not really mention whether it's going up or down. But I believe it is this is the right one. And then we define a very important energy called charging energy. I forgot to write here. Do you see that this is 2e squared divided by 2 summation, C summation? And this is the energy when you charge the capacitor by 2 electrons or 1 Cooper pair. Because this is Q, half Q squared divided by C, right? So this is the energy you need to charge the capacitor by 1 extra Cooper pair. Make sense? With that, we have a very simple Hamiltonian. It is H equal to 4C times M minus NG squared minus EJ cosine phi. N is talking about the extra Cooper pair you have in that island. NG, you can say that is the background charge, the extra Cooper pair due to the gate, right? And I already told you that when you change the gate voltage, you are going to have effect to change the Cooper pair in this island. This is called the island. So the total Hamiltonian is this. I just want you to be very careful when you read papers. Sometimes they define the EC, right? Some papers define EC as the charging energy of a Cooper pair. The charging energy of 1 Cooper pair. So I actually what did I say just now? This is the charging energy of 1 electron. Did I say Cooper pair now? I think I say something wrong, right? Because EC defined as E squared divided by 2E summation, C summation. So the charge is Q. So EC is the charging energy of one electron. Sorry, do you follow me here? I said something wrong. EC is E squared divided by 2C summation, right? Q, half Q over V squared is the energy, right? So because EC is E squared divided by 2E summation, that's why I have a 4 here, right? So this is the charging energy of one electron, okay? But some paper, they also use EC, however, it's the charging energy of a Cooper pair, so 2 electrons. So it is actually 2E squared, which is 4 times of the EC we have here. In that case, you will find that the paper will write the Hamiltonian is EC instead of 4EC. So don't get confused. Sometimes you see there's a 4 difference, then you know that when there's 4, it means they're using EC as the charging energy of 1 electron. Otherwise, it is 2 electrons. Right? We will see this in later. Okay. Now, so this equation is easy to memorize. In principle, I can just give you this and tell you, hey, this is the Hamiltonian of a Cooper pair box. It is equal to the charging energy of a Cooper pair, and then times how many pair you have extra. You have 1 extra, 2 extra, then it becomes a square, right? Because the energy is just go up with the number of Cooper pairs, right? And then minus the potential energy that, plus the potential, and because it's negative, but it just plus the potential energy of the inductor, right? Now you look back, this also kind of makes sense. So its Hamiltonian is how much you store as a capacitive energy plus how much you store as the inductive energy in the Josephson junction, which is a nonlinear inductor, remember? So now we have 2 very important quantity, EC, right? Let me repeat this. EC is the charging energy. You will see this very often. Right? This is the most basic thing when you talk about the Cooper pair box or superconducting qubit. And then Josephson energy. These 2 energy is going to change many things and also change the type of qubit you have. And when you are doing the energy participation ratio, you are going to use this also. Okay? Any questions? Right, so I gave you the derivation, a lot of math, no need to memorize, but I hope you can memorize the procedure, appreciate it. Equation of motion. Then, because from there we get the generalized velocity and coordinates, then we can get the Lagrangian. Then we can get the Hamiltonian. And then we can quantize this by promoting to the higher, promoting to the operator, right? And finally, this is the equation, just the charging energy plus the Josephson energy, which is expected, right? Even we did not go through all this derivation. And then I talk about the meaning of the Hamiltonian. And if you look at this equation, you can imagine if I have a very large EC, I kind of can ignore the EJ, not ignore, but I mean, it becomes less dominating, right? If I have a large EJ, this term is less dominating. Now, what is NG? NG, of course, is great because we use it to control the qubit. But it also means that what if I have noise? Any noise can be modeled as something like this, right? If I really want to model it, I will erase it later. But isn't that I can, I can have a noise like this. This is the noise. This plays exactly the same role as the CG, right? Coupling. Or maybe noise come from here, right? Then you use CG to do the coupling, right? So this is called charge noise. So if I have some noise, for example, like what people call two-level defect, right? Is that right? Two-level system, right? Two-level system. In your structure, you have this oxide superconductor, and you have a lot of defects. And if they are going to change the states, when we're saying to change, so if the atom can change their configuration, actually, they can hopping around from one state to another state. That can cause some problem. So if we have a small EC, when the EC is small, right? Then you see that if I change the NG, this is NG, this is not the coordinate, then you have very different energy level for the first level and second level. This is 0th level. Then it means your 0 and 1 state gap is very large. Then you have a problem with your qubit, right? But if the EJ is very large, in this case, a little bit change in NG does not change the Hamiltonian too much. That's why I have a pretty constant level regardless of the background charge. So then I have a less noise, right? Charge noise. So that's why this regime is called the Transmon qubit, and this regime is called the charge qubit, right? And how do I have a small EC? EC again is charge divided by capacitor, right? Charge square divided by capacitor. Let's look at this. This is EC, right? So what I can do is to shunt it with a large CS. Then I have a very large C summation. And then I have a large C summation part. Then my EC will reduce. So that's why a transmon is a Josephson junction in parallel with a large capacitor. Yeah.
It's only roughly the same energy gap for some subset of them, right? Because it's not actually a harmonic oscillator because it's cosine instead of parabola. Is that correct?
Oh, yeah. Do you see that this 0 level to first level, this is the H omega 1 0, right? This is from 0 to 1, so it's very different. It's not harmonic oscillator. Oh, good.
It looks the same, but in reality, they're slightly different, right? So
They need to be slightly different. You're right, right? So what he's trying to say, this one I have very good enharmonicity, right? Because from 0 to 1 and 1 to 0, I have very different energy. But when you go to Transmon, looks like they are the same. Indeed, they are much closer than this one, and that is a trade-off. So I did say here, when you have a Transmon, you might not have enough enharmonicity, right? So you may do something in between. Okay? Yeah.
are N and the phase,
Yeah. Yeah, they are the canonical conjugate variable. So that is what he's trying to say. So eventually we come up with this equation, right? Originally, what is n hat before we divide it by q, 2q? The charge, right? The charge is the momentum, right? Generalized momentum. And this is like, this was the flux, right? But now it becomes the phase and the lumbar. So lumbar and phase, again, they don't commute with each other. If you can measure the number of charge accurates, then you will lose the phase information. And if you can measure the phase accurates, you lose the number information, right? Now, so I did not go through this. Maybe I can put in assignment. You will find that e to the power plus minus phi n is just a raising and lowering operator, right? So this one I really just jump, right? And if this is the case, then e to the power I phi can be represented as n plus 1 and n outer product. Because you think about this, I apply this to n, then this one becomes 1 because they are the same, right? Then it promotes when this apply to n, it promote it to n plus 1, right? So this is a way to write it. And why do I want to go through, and similarly for negative I phi. Why do I want to go through this? Because now I want to expand cosine phi as the sum, the average of these two numbers. And then with this one, then I will be able to write down the, write it down in the matrix form. Okay. Now here you again actually see some intuition. Now this is very rigorous, right? Because we start from equation of motion. Eventually we have the Hamiltonian, and then we divide it by 2e. We get the phase and the number, and then these are still all very rigorous. Eventually the Hamiltonian turned out to be the summation of different number of excess Cooper pair in the island, right? So this is diagonal, and then some off diagonal term. But now if you try to think from the point of physics or intuition, this again is the charging energy at different given eigenstates, right? And this is talking about the energy, kind of like the energy I need to bring the one more extra Cooper pair, or take out another take out one Cooper pair from the island, something like that, right? So are you okay with this formalism? I mean this equation. Let's look at it a little bit careful, right? N start from 0 to infinity. So what does it mean? I have 0, 0. Because I express in the eigenstate basis of n, 0, 0, then the energy is 4EC 0 minus NG squared when it's 0, 0, right? So here it is not 0, right? Last time when I write it, what I mean is it has some item here. When this is 0, 0, for example, this 0, 1, 2, right? For example, this one is 2, it means this is E4 EC 2 minus NG squared, right? 4, this is 4, 2, 2. Do you see that? It's diagonal, right? And then you have some off diagonal term along here, which is EJ divided by 2. Say again. After the square term, you mean this? This one? Oh, here? Okay. This is English 4, sorry, for my writing. I mean, this is, I just want to highlight that the value is this term, and this corresponds to 2, 2 state. Because this is 0, 0, right? This is 1, 1, this is 2, 2. Diagonal. Yeah. Okay, so I finished the review. Now let's continue. We were going to use this equation, right? So now